Hello, my name is Thomas. Today I'd like to talk about 3 ways to find the Riemann sum in calculus. So to find the Riemann sum is to approximate the area under a curve using rectangles with non-infinitesimal given widths. The width is usually given in AP tests. Right below the text, I've also drawn a sample rectangle that's used in Riemann sum with its length and width in terms of A and B. And close approximation of the area under the curve is actually the accumulation of the area of several of these kinds of rectangles with the same or different widths. However, using the same width is usually easier because you can actually factor it out when you are taking the sum of all the areas. But since it's an approximation, it doesn't really matter if the widths are the same or not. Let me draw a couple more rectangles to show you what's the concept of accumulation of areas. So I've drawn 2 more rectangles, one is slightly bigger and the other one is slightly smaller, and they have areas represented by the capital letter A, B, and C. So the exact area under a curve, which is the part that's colored blue, is equals to the sum of all the areas of the rectangles, which in this case will be capital A plus capital B and plus capital C. So here just some introduction. So now it's all about rectangles. You may ask, how should I draw a rectangle? There's actually 3 techniques: the left-hand point, right-hand point, and the midpoint method. Let's talk about left point method first. What left method really is to take the y value of the left boundary of the rectangle as the rectangle's height. So what does the rectangle look like? Suppose I have a function that's strictly increasing during an x interval. A rectangle on this graph will look like something like this. I draw a couple of it just to show you how, in real application of Riemann sum, how the rectangles will look like. As we can notice right here, all the left boundary are touching with the function. Therefore, suppose one of our rectangles has a width of b and the height of a, and its left and right boundaries, are represented by x1 and x2. The area of one of the rectangle will be b times fx1. You may pause the video and think about it for a second. So let me explain why the formula of the rectangle's area is like that. We have our width, which is b, right here, and fx1 is in fact the left boundary, the length of the left boundary of this rectangle. And that's how we get the area of one of our rectangles. If we look closely into the graph, we will find out our approximation is actually an underestimate. Why? Because the graph is strictly increasing. So I have another graph right here, it's also strictly increasing. You will find out that all the left point rectangles that we have drawn is always below the curve, which means that the sum of all the rectangles will always smaller than the exact area under the curve. On the other hand, if you have a strictly decreasing function, you will find out that all the left point rectangles that we take are above the graph, which means that their approximation of the area under the curve will be an overestimate. So now let's do a right-hand estimate. I've still used x1, x2, a, and b as parameters for the right-hand rectangles we're dealing with right now. Our area right now will be a times fx2, because now we're using the y value on the right bound of the rectangle as the height of the rectangle. Be careful that in the right-hand Riemann sum, when you're estimating a strictly increasing function, the Riemann sum, the estimation will be an overestimate, which is an exact opposite of left-hand Riemann sum. But for a function that is strictly decreasing, the right-hand Riemann sum will be an underestimate. And finally, let's talk about the midpoint Riemann sum. It is the most precise approximation of the area under the curve, but it's also the one that's taking the most effort. So suppose I'm taking the midpoint Riemann sum of this graph. I'm not taking fx1 as the height of the rectangle, which I will do in left point Riemann sum, and I'm not taking fx2 as the height of the rectangle, which I will do in right hand Riemann sum either. Well, what I will do here is to find the midpoint between x1 and x2, and its x-coordinate will be their average. So x3 equals x1 plus x2 divided by 2. That's how we calculate an average. So now we have our x3, which is our midpoint. In the next step, suppose we have x2 minus x1, which will be the length of the interval, equals to a. We want to set the height of the rectangle equals to the y value at x3, which will be fx3. So the area formula of our rectangle will be a times fx3, where x3 equals to the midpoint in between x1 and x2, and they're respectively the left and right boundaries of this rectangle. The reason why the midpoint Riemann sum is very precise is that if you take a very close look at the graph, that you can zoom in into the top of the rectangle, you will find out that at a very close look, which means that the rectangle will also has a very small width as well, but not infinitely small, the function will actually behave linear. So if you take this chunk out from the rectangle and add it to here, so it will be something like this, you'll find out that actually the total area of this shape is a very close approximation of the area under the curve, and that's why the midpoint method has high precision estimating the area that's under the curve. That's the math of today. Thanks for watching.